All right, let us do organic chemistry because frankly, we're out of chapters. All right, so we're going to talk about organic chemistry. We're obviously not going to touch tremendously deep into it all, but we'll get a nice overview so I could just send you on your way to organic. All right, so organic chemistry is the study of carbon. Thank you. The end. All right. All right. See, look, first sentence is a study of compounds that contain carbon and other elements. So really the basis of organic chemistry, compounds are compounds that basically have carbons attached to other carbons. And for the most part, a lot of hydrogens attached there as well. And that is typically sort of the connection that you got going on. Which are carbons attached to carbons and carbons attached to hydrogens. And along the way, we do sort of replace some of these hydrogens with other elements like oxygens, nitrogens, which give us some different sort of classes of organic compounds. Couple of things about carbon, as we hopefully know, right? Carbon and the hydrogen bond is a non-polar bond, right? And obviously the carbon-carbon bond is non-polar as well, which means a lot of organic molecules are non-polar. And that's why a lot of sort of the early organic guys, for example, like methane, propane, butane, there are a lot of them are gases because they're held together by really weak intermolecular forces. So there is a difference between an organic compound and an inorganic compound. Inorganic compounds are like things like sodium chloride, and they're held together by, for example, very strong intramolecular forces. So when we have something like sodium chloride, that is two ions that are basically held together by an intramolecular force. That is the electrostatic attraction. It holds obviously the two ions together. And that's different than really our intermolecular forces, as you may remember from your Chem 50 days. We have things like hydrogen bonding, right? Which is a bond between hydrogen and nitrogen, oxygen, or fluorine, right? One of those electronegative elements. We also have dipole-dipole interaction. And that is essentially what polar molecules use that cannot hydrogen bond. And obviously, hydrogen bonding is what polar molecules use that have the ability, obviously, to hydrogen bond. And by the way, in order to hydrogen bond, even though organic molecules have tons of hydrogens on them, they're all nonpolar. They're not directly attached to a nitrogen, oxygen, or fluorine, which means even though they have lots of hydrogens, they cannot hydrogen bond. It does need to be directly bound to the nitrogen, oxygen, or fluorine to be able to do that. Most organic compounds use what are sometimes referred to as dispersion forces, and those are very weak forces that nonpolar molecules use. Those usually result from some type of instantaneous dipole. Electron shifting one way or the other causes a temporarily change in the sort of neutral molecule it is, and you get sort of a separation of charge. As you may also remember, all intermolecular forces pretty much is the basic interaction of the positive side of one is attracted basically to the negative side of the other. In the case of hydrogen bonding and dipole-dipole interaction, you typically have polar molecules or a polar part of a molecule that always has sort of a fixed dipole, so it's always ready to interact. Things that are used dispersion forces, like a lot of organic compounds, they need something to happen to have the electrons shift around, which is what is referred to as polarizability of those electrons to shift one way or the other. To create a positive or negative side for them to interact with each other. You could also induce a dipole by having a ion near it or a polar molecule to do that. So because of that, things like sodium chloride, for example, are held together by very strong intramolecular forces, which are the forces within that one molecule. And that means that they typically are going to be solids at room temperatures and non-flammable. You can heat the heck out of sodium chloride. You'll never get it to pop into the gas phase under normal conditions because it's held together so strongly. It'll just start to melt before it actually kind of pop out into the gas phase. And that's different than, say, like methane or butane, which relies upon dispersion forces, which is really the weakest of all intermolecular forces. This is, by the way, the strongest. And because they use dispersion forces, they're held together not very strongly, which means if you look at them wrong, they're just going to pop off into the gas phase. And that's, again, why things like methane, butane, propane, right? These are all gases under normal conditions. It's also why when you take organic chemistry, they'll not actually in the fume hood, but you'll use a fume hood. Maybe they will. I don't know. It depends on your teacher, I suppose. But work in a fume hood because a lot of organic material compounds are held together by these weak dispersion forces, which means even if they are a liquid, it doesn't take a lot of convincing for that liquid to go into the gas phase and create vapors, which is what volatile means. And a lot of those are also very flammable as well, which is usually you don't want like an open flame near any of those things if you happen to be using them. So all organic compounds really have the carbon as the basis. And let us remind ourselves of our friend carbon. It has 4 valence electrons, as it is group number 4 on the periodic table. And pretty much an important thing to remember when you take organic, or if you take organic, or if you just happen to pass by an organic room that somebody's taking it in, carbon should only have 4 bonds and no more than 4 bonds. And sometimes when people first start to take organic chemistry, they get a little overzealous with the bonds, and before you know it, carbon's got like 42 bonds to it, and also some lone pairs just to make sure you got everything correct there. So it should only have 4 bonds. Very rarely, there are a few cases, but very rarely will you see carbon with actual lone pairs on them. They usually will continue to make bonds until it has 4. So that's usually a really good thing to kind of keep in mind. And that's sort of the basis of how you draw a lot of things, is to get carbon to 4 bonds. And a lot of times, if there's really no other element or anything else attached, usually those bonds are made up by attaching hydrogens. It's basically kind of what goes into those places. Also a reminder, right, you do still obey the octet rule, right? When you're dealing with organic chemistry, that means should not go over 4 bonds because that's 8 electrons. That also means our friend hydrogen should only have 2 electrons total, right? Or 1 bond. So just like when you did with Lewis structures, you won't put hydrogen in the middle. They're always going to be on the outside. And frankly, hydrogen should pretty much always look like this. Also should never be double bonded, triple bonded, and dots all the way around or anything weird like that people like to do. So you want to always make sure that it looked like that. And obviously here's our methane, which is really the simplest organic molecule you could have, 1 carbon and 4 hydrogens that's attached there. Carbon likes to form single bonds. It also will form double bonds or triple bonds, again, to meet sort of the octet rule. To do that, every time though that we do sort of put a bond on in organic chemistry between 2 carbons, it usually involves a sacrifice of 2 hydrogens, 1 on each of the carbons within the bond. So this is ethane, which is an organic group that are known as alkanes, which are single bonded carbons. Bless you. When we go to put on a double bond between these 2, we cannot just slap a double bond on there. Otherwise, again, everybody will have more than 8 and be over the octet rule there. And carbon, right, as much as you might want it to do so, can carbon go over 8? It cannot. And the reason things can go over 8, by the way, is why? So it's like it does. So it's because right there where sulfur is on the periodic table, right? If you go to the right or left of it and down, that's the 3rd energy level, right? And those guys have d orbitals available to them, right? N equals 3. That's where you first start to see the d orbitals come in. And because they have those orbitals available to them, that's why they are the ones that can kind of do the expanded octet. because organic chemistry is carbon-based, carbon is the second energy level, right? N equals 2. There are no d orbitals to be found, which is why, again, they cannot really ever go over 8 and stuff like that. So that's why you typically don't go over 8 here and have that expanded octet when you're dealing with organic compounds, because really the backbone of pretty much of all organic molecules are the carbon sort of backbone. So to do this, we do have to sacrifice a hydrogen on each of the carbons to put our double bond into place here. And this creates what is referred to as an alkene, ENE, and that is a carbon-carbon double bonded compound as opposed to a carbon-carbon single bonded, which are alkanes. And obviously, if we were going to make a triple bond, once again, we have to kind of make room for it by removing 2 more hydrogens to make our triple bond here. This creates a organic class of molecules known as alkynes, YNE, and those are carbon-carbon triple bonds basically happening. These are what are sometimes referred to as the functional group for organic molecules, and the functional groups are basically the part of the organic molecule that basically tells you what type of organic compound that you are dealing with. By the way, just to see how these names work, this is ethane, ANE, because that's an alkane. This also has 2 carbons, which if we do the non-common name, that is ethene, ENE, which has 2 double bond. And if we don't use the common name here, this is ethyne, YNE. They're all based off of the alkane name. So pretty much a lot of the nomenclature that you do in organic chemistry comes from the simple organic molecules, the alkanes, the carbon-carbon single bonds, and everything kind of goes back to those. So usually when you first start organic chemistry, you want to learn really the first 10 alkane names, and everything sort of funnels back to that in terms of how other things are named. You just do slight different tweaks along the way as you go through it. So speaking of that, obviously, let's throw back a little of general chemistry here as well. When we have something like methane here, and we wanted to do something like our friend hybridization, right? This carbon here is sp3 hybridized, yeah, because it has basically 1, 2, 3, and 4 electron pairs, yeah. If you're not good at assigning hybridization, here's the simple way to do it, which maybe you were taught or not, I don't know. So there's an S. P's have 3, right? And D's have 5. So basically, you count up electron pairs like you're doing Lewis structures, which means if you have a double bond or a triple bond, it counts as 1 electron pair, and you just mark it off. So that's 4 electron pairs, 1, 2, 3, and 4. That's an sp3 hybridization that is happening. Obviously, if we had our double bonded guy here, and I put too many hydrogens there, so that's why they invented an eraser, I suppose. There we go. There we go. We look at this carbon, for example, here it has 1 electron pair, 2 electron pairs, and 3 electron pairs, as a double bond would only count as 1. So again, 1, 2, and only to 3 right about here. So that's an S and 2 P's, which means this is sp2 hybridized. Same thing with this carbon, it's identical on this side. It'd also be sp2 hybridized. In terms of geometry, right, something like methane here has 4 electron pairs and also 4 bonds. So that is your tetrahedral geometry, right? Molecular geometry, 109.5, the bond angle happening. Here, though, it has, again, 3 electron pairs and has 1 bond, 2 bonds. And again, the double bond counts as only 1. Which would give you 3 bonds. The geometry changes as you put the double bond on. It now is something like trigonal planar, right? Or triangular, which is a bond angle of 120 in that particular case. And it changes even more as we slap on our triple bond here. Looking at this carbon here, it has 1 electron pair. Once again, the triple bond will count as 1 electron pair. So that's going to be an sp hybridization. And it also has two bonds, which means we now switch to linear in terms of our geometry, which is 180 degrees. So these are the typical sort of geometries that we see occur here, our tetrahedral and sort of our alkanes. We get some trigonal planar, and then it actually levels out. It kind of becomes linear, a straight line as we continue to put bonds on. Again, every time we put that extra bond on the carbon, we do sacrifice two hydrogens along the way. So this is basically what we see in alkanes, which are single bonded guys, alkenes, and alkynes, right? Any questions on hybridization here? Obviously, to get into something like sp3d or sp3d2, you would need an expanded octet, which again, you might not come across here in organic. Let's talk a little bit about some characteristics of organic compounds. Again, something like methane is the main component in natural gas. Ethylene is used for plastics. Some compounds have chains of atoms and some have rings. So when we look at organic molecules, there's kind of two sort of situations, or a few situations. We can have something like this, which is sometimes referred to as a straight chain, which basically means it just runs straight across. There's also situations where you may have several carbons that go straight, and then maybe off of it, like branches, you have what are sometimes referred to as branch chains. And, you know, it's got some branches like a tree kind of hanging off of it along the way. So something where it's just not straight across, but does have kind of points where it dissects out into other directions, or sometimes referred to as being branched. And we could have ring type structures like what we see here, which is cyclopropane, which is typically drawn more of a line structure, or like a triangle basically. And when we draw line structures, by the way, anywhere sort of lines come together or end, there are carbons believed to be there, and the appropriate number of hydrogens, which in this case, as we can see on the other one, each of these guys have two lines coming in, which means they need two hydrogens to get our carbon to 4 bonds. But typically something like cyclopropane would just be drawn as a triangle in this case. And line structure and condensed structure and expanded structure is what we actually see on this page. So this is what is sometimes referred to as the expanded structural formula. And basically all that means is you draw out the hydrogens. Over here, something like this is what is referred to as condensed formula, where you basically don't draw out the hydrogens is pretty much it. And you could have line structure or line formula, skeletal structure, whatever people call it these days, but I used to call it line structure way back when I took it 7 times. This is what it looks like. It's basically just a bunch of zigzag lines. And again, everywhere you don't obviously draw the carbons in, but these are all carbons here along the way. And once again, there should be the appropriate number of hydrogens at each of those points. So it's just sort of a zigzag back and forth mountain range type of deal. And obviously it's minimalist, so it doesn't get so crowded there. You also may even see a line drawn like that, which is just a carbon at the end of it. But if you do see a line drawn and they want something there, they will write it in like OH or something like that. So, and that would make that like an alcohol or something like that, I would suppose. Well, I just draw there 1, 2, 3, 4, 5, 6, 7. So something like 2-heptanol would be what I just drew there, which is an alcohol along the way. So those are 3 very common formulas or structures or way that they are represented in organic chemistry there. Any questions on that there? So as I mentioned before, organic compounds may also contain other elements besides carbon and hydrogen. So that's really how we get a lot of our sort of functional groups, is we sort of substitute out some of the hydrogens, and in their place, things like oxygen is very common in a lot of organic compounds, nitrogen containing compounds, even sulfur containing compounds. And a lot of the halogens from group 7 find their way into a number of organic compounds along the way. Very common sort of arrangements that we see for these things is what we see in this table here. Carbon, again, making 4 bonds. We do see oxygen here, sort of like a lone pair like we see in an OH sort of bond. We can also see nitrogen, which usually has a lone pair of electrons on it. We could also see some double bonded carbon as well to the oxygen. This is what is referred to as a carbonyl group. Carbonyl carbon. And this is also a polar sort of bond, oxygen being more negative, carbon being more positive. So although the basis of a lot of organic compounds are nonpolar carbon, hydrogens, as you go through different sort of organic groups and you substitute out these hydrogens for different elements, you can turn part of the molecules into being more polar than nonpolar. So a lot of organic molecules will kind of have 2 parts to them. They'll have sort of a nonpolar part and a part that's sort of polar as you go through some different groups. And that does affect things like how they interact with things like water, how they interact with themselves as well. So it is possible for organic compounds to be able to do things like hydrogen bonding because they do contain like an OH group, and also be able to be soluble in water as well. If they have certain groups attached. So we sort of change some of the characteristics of organic compounds as we go through the different groups, and depending on what elements are present, gives them, again, some different sort of features. Like this OH group here on methanol here, which is our alcohol, that is the same polar group that we see in water, where this guy's more negative, this guy's more positive, which means that when you take something like methanol and water, they have really no problem hydrogen bonding with each other and being soluble in each other, because the way that methanol will be able to interact with itself is through hydrogen bonding, and it's able to interact well with water the same way. And that is the idea of like dissolves like that you might have heard when you talked about solubility. Things that have similar types of intermolecular forces will be able to be soluble in each other. So that's why polar things and polar things are soluble in each other. Non-polar and non-polar things, right, are soluble in each other because they can interact really well. To that end, though, as we may talk about a little bit, or as you'll talk about as you go through your organic solubilities, for example, something like solubility does start to decrease as the non-polar side of the molecule gets much larger. So it kind of gets in the way of everything. So at some point, you'll just have a really big non-polar part of that molecule and this very small part that's able to interact with, say, water. So although something like methanol here can interact well with water, if you bumped out like, 9 carbons, all with hydrogens, or however many carbons I just drew there, all with hydrogens, and you still have this OH group, this giant part of the molecule now is much larger, and it doesn't make it work very well with water because it gets in the way of getting that OH group and allowing it to interact well with water. Plus, it's now super large. So in order for something to be soluble in water, you have to replace water and water interactions with something that's very similar in size and in terms of interaction. So now it's not going to fit very well when water and water interactions come together, and it's going to be actually non-polar. So typically speaking, with organic compounds, even if you have something like an OH group, which helps with solubility, if you hit about 5 to 6 or more carbons, solubility with water starts to drop off to pretty much nothing because of all that non-polar part of the molecule. As I mentioned before, condensed structure is essentially where we just kind of shorten the formula there. We do not draw out our bonds to hydrogen, and it's commonly used. A lot of people, when they do draw condensed, usually will still put the dash between things. So that's common as well to sort of see it like that. Also, if you have a really long run of the same unit that repeats, you'll sometimes see something like, maybe something like this. And that 4 means that you have 4 of these units basically repeating one after the other. So this guy would have 1 carbon, 4 more carbons, and 1 more would be 6 carbons that it essentially has in this case. Some lines can be drawn to show sort of how groups are attached. So there, as you can see, you have that group kind of above, and that is because sometimes if you kind of throw it in here, it's not very clear as to where it's attached to and stuff like that. In addition, sometimes people get confused when they look at this in condensed formula, say something like this. Again, here, the connection is carbons to carbons with the hydrogens attached to the carbons, although in condensed formula, it is drawn sort of with the hydrogen attached to the carbon, attached to the next carbon. It actually does look like that. So although it does look like maybe the hydrogens are in the middle and have way too many bonds, because they can only have that one bond, they are actually on the outside when you actually do draw it out. All right, so we got that. As I mentioned before, line structure very commonly sort of used, which is sometimes a skeletal structure. And you can do it, like I said, like this. If you have a double bond, you could actually just throw a double bond in there. If you had a triple bond, you could throw a triple bond in there. Some people will then draw it straight because technically speaking, the geometry changes, but you'll sometimes see it even drawn the other way, even still with the zigzag sort of way as well. A reminder that basically when you're drawing things and getting there, as we talked about, it is the idea there's carbon needs 4 bonds. And if you're all out of other elements, pretty much you're going to fill in with hydrogens to get carbon to 4 bonds. Is pretty much what you do. So here is cyclohexane here. And if you take organic chemistry, you will be able to draw this very well, I suppose. It's not bad for my first try there. So you'll be good. And you draw it a lot. There's cyclohexane, there's benzene, which is basically based off of the same sort of structure. So you oftentimes will see benzene that looks something like this. It's got 3 double bonds happening there as well. Now, when we do draw it and you do draw a line, we will include also the group there if it is something other than carbon at the end. So you'll have something like this. This is a alcohol, and it's an alcohol because of that is the functional group for an alcohol, which is the OH group. And for example, this is something like cyclopentanol, OL, and it has that OH group there on a ring. So we've been talking a little bit about the functional groups here. So functional groups in organic chemistry, as I mentioned, is really the part of the molecule that gives it or makes it a certain type of organic compound. It is also in a lot of cases when these organic molecules go through some type of reaction. That's pretty much where everything happens, kind of right there at near the functional group is sort of where things basically happen. You'll also sometimes see R dash something. R is used in organic chemistry as just a generic letter to represent a carbon group that's attached to it. So some type of carbon group that's attached to it. And then we have our functional group that is there. So if you see something like ROH, that's an alcohol. And again, that means just some type of carbon group that's attached to it. So let's talk about some of these functional groups a little bit more. So first off, hydrocarbons are compounds, much like the name implies, that contain only hydrogen and carbon. So for example, if we had something like we were looking at there, these are all just carbons and hydrogens. This is a hydrocarbon, and line structure would look something like that. So it looks like a V, I suppose. And this is also sometimes referred to as a saturated hydrocarbon. And saturated hydrocarbon essentially means that each of those carbons have the maximum number of hydrogens that it can have to get to 4. So each of those have really the maximum hydrogens you can put on there. And it usually happens in an alkane situation where you have carbon-carbon single bonds. So that's going to allow basically the maximum number of hydrogens to basically be on there. Alkanes have a functional group. Some people call it a functional group of carbon-carbon single bonds. They're all single bonded. They're really the basis for all other organic compounds. Pretty much most things will come back to alkanes. Alkenes have a carbon-carbon double bond as its functional group, and it's got to have at least one double bond in there. Alkynes have a carbon-carbon triple bond as its functional group. And aromatic compounds have benzene as its sort of functional group. So somewhere there is benzene, which is what I drew a second ago. Once again, it has 3 double bonds. You could also draw a resonance structure where your double bonds move to the other side. Or maybe if you're not taking a true organic class, they'll sometimes even see a circle drawn in there, maybe in a real class as well, they'll do that. And that implies because those double bond electrons are delocalized, so they could be moving around the ring. So sometimes benzene is represented with a little circle there in the middle, but it still does have 3 double bonds, which means each of these carbons actually has 1 hydrogen attached to each of them. There's a hydrogen at each of these spots. And again, that gives each of those carbons basically 4 bonds, which is what it needs. So here's our groups here. Got our single bonds, our double bonds, our triple bonds, and our aromatic compound here. Some other functional groups that you might come across: alkyl halides. That's a fancy way of saying that's a carbon that has a halogen attached to it, right? Alkyl is carbon. Halide is a halogen, right? So that's basically a carbon group that has a halogen attached to it, like CH3Br here. Alcohol's functional group is the OH group, and that's a very polar group. An ether has typically a carbon-oxygen-carbon run. An amine is actually a nitrogen-containing group, and it is an NH2. Amines are basically derivatives of ammonia, which is NH3, a weak base. So a lot of amines can act like ammonia, like a weak base when they react, but they'll have that nitrogen. Thiols are the smelly ones. That is sulfur base there. So it has SH group is the functional group for a thiol. So each of these things are named differently. Each of them will have some different properties in terms of solubility, how they interact with other things based on the functional groups that are present. That carbonyl group, as I mentioned, is a very important part of organic chemistry. It is a polar sort of group. And this, again, is sometimes referred to, as I mentioned earlier, a carbonyl carbon. And a lot of reactions and mechanisms, which is a lot of what you'll learn in organic chemistry, involve like attacking this thing and breaking it open, electrons moving. When you talk about mechanism in organic chemistry, it's a lot about where electrons go, how they move, how things and elements sort of move over from one side to the next. So there's a lot of looking at that and following that through. Some of these other functional groups actually do have that carbonyl group. So the aldehyde group has the carbonyl carbon and also a hydrogen. And once again, this group, because it has the hydrogen, will always be found there at the end of the molecule. Because of the hydrogen, it can't be inside. And that's different than a ketone, which always has sort of a 3-carbon run with a double bonded oxygen in the middle, which means you'll always find that carbonyl group never at the end, because you need the 3 carbons with it being in the middle for it to be there. So ketones and aldehydes. Carboxylic acids have this as the functional group: carbon oxygen double bond and an OH. That oftentimes in formulas is written like this. We're very familiar with a carboxylic acid. It is our friend acetic acid. Yes, that is vinegar. Yeah. So that is a carboxylic acid. It looks like this. And that is the acid part of it. That is the H that goes off when it becomes acetate and it releases it. But that is an organic functional group, the carboxylic acids. An ester looks like a carboxylic acid, except that it has a carbon and not the hydrogen. And a carboxylic acid, I'm sorry, an ester is actually made from a reaction of a carboxylic acid and alcohol. Is sort of how you make an ester. Esters are responsible for things that smell, like, the smell of bananas, pears, fruits, oil, wintergreen, all those type of things are all esters. And a lot of pineapple, for example, are all responsible as esters. So when you get to that lab, you gotta go smell things, perhaps. Don't smell too much. And the amide here is really a carboxylic acid with an amine hanging off of it there. So it basically looks like that. Not surprisingly enough, that's how you make it. You take it, you put them together, and you get this sort of group right here. This is also the bond, as you might remember or know, is like a peptide bond. Yeah. So that is the bond that happens when like amino acids come together. Yes, right there, breaking apart. So that is the bond that you see when some amino acids actually come together. So these are all the different sort of functional groups of organic molecules. And again, each of these give them, as I mentioned, different properties. You name them slightly different along the way here. So let's talk first about alkanes and how we name them and kind of work with them. So alkanes are hydrocarbons, which again have only carbon-carbon single bonds. They have the general formula of CnH2n plus 2. N is the number of carbons. So for example, if we had one carbon, 1 times 2 is 2 plus 2 is 4 hydrogens. And that is our friend methane. If I had 2 carbons, 2 times 2 is 4 plus 2 is 6, would have 6 hydrogens. That is my friend ethane, A-N-E. If I had 3 carbons, and that would be 6 plus 2 is 8. That would be my friend propane. 4 carbons would give me 10 hydrogens. That is butane. 5 carbons, 12 hydrogens is pentane. At this point, it kind of goes with the prefixes like penta, hexa, hepta. 6 carbons would give me 14 hydrogens. That's going to be hexane. 7 carbons gives me 16 hydrogens. That's going to be heptane. 8 carbons, 8 times 2 is 16 plus 2 more is 18, is octane. 9 carbons, going to give me 20 hydrogens, is nonane. Why not? Could be making it up. C10H22 is our friend decane. So these are the first 10 alkanes. These are all single bonded. These are all put together by carbons attached to carbons and pretty much hydrogens on the outside there. Everything pretty much in terms of nomenclature will go back to these first 10 names, a lot of it. So really, if you learn these very quickly, it'll make a lot of your life easier in terms of at least the naming part of it, because again, you just kind of do some slight variations along the way. As I mentioned before, saturated alkanes have the maximum number of hydrogens, and again, they will have all single bonded, so they'll have that maximum number to get carbon to 4 bonds in this case. These are what sometimes referred to as acyclic, which means they're not a ring structure. They just kind of run straight. Again, you could also have, as we will see, cycloalkanes. And cycloalkanes are ring structures like we saw with our cyclopropane, which is basically our 3 carbons that close up on each other in this case. They are all alkanes, and as you can see, the ending of the name is ANE, so that all goes together. And for the most part, I won't say all functional groups, but a lot of functional groups, the way that they you end the name of how you name it is very similar to the actual functional group's name in terms of how it ends. So as I mentioned, cycloalkanes, because they are actually a ring structure, they actually do lose a couple of hydrogens, because when they close up on each other, they have to make that extra bond. So they actually have the general formula of CnH2n H2N. So if I had my 6 carbons, I would only have 12 hydrogens in this case. And that is what we see here in this picture. We have our 6 carbons, which is at each of these points. And each of these guys have 2 hydrogens attached. And that will give each of those carbons 4 bonds. And that is where our 12 hydrogens basically come from here. How we go about naming it, as I mentioned there a second ago, pretty much you put cyclo in front of the alkane name. So this is 6 carbons, which is basically hexane. But because it's a ring type structure, it becomes cyclohexane. So you kind of put cyclo in front of it when you go to name it. Any questions on that there? All right. So all alkanes will end with that ane suffix, and here again is our structural formulas for each of them. The way that we name alkanes is usually in organic chemistry. The sort of official way that you name things is through the IUPAC name, which is the International Union of Pure and Applied Chemistry. The 3 guys that get together to tell you how to name everything in someplace in a hidden location. That's right. They're in a hidden location. You're not allowed to talk to them. What you'll also see when you take organic is there's a lot of different names for the same thing. So there's like the official IUPAC name. There's the common name that Joe calls it, and there's the historical name that everybody's just called it for a really long time. So that's how you get something like 2-propanol, which is also isopropyl alcohol, which is also rubbing alcohol. So it's all the same thing. So there's a lot of crossover in terms of names. There's a lot of historical names and common names that are still used today a lot. But most of the time, probably you want to shoot for usually the IUPAC way of naming things, and they have very strict rules about how you go about sort of naming things. So let's talk a little bit about if we wanted to name something, for example. So let's take a look at like look at something like this, and just to give an idea of a nice simple one here to start with. So if we had an alkane, for example, and we wanted to name it, and pretty much if you wanted to name anything, and this is what I just drew here is our condensed formula. We could also draw this. It looks something like this, and line structure as well. So if we look at either of these here, what we're looking for is always when you want to go name something is you want to count or find the longest carbon chain. So you want to find the longest continuous carbon chain. It does not always has to be the straightest. It could go straight, it could go up, it could go over to the right. The only thing that you can't do when you're counting the longest carbon chain is go backwards. So kind of has to go in one direction till you hit a dead end and figure out how many carbons that was. And what you're looking for is really the longest continuous carbon chain. So for example here, if we were to look at this simple one here, the longest carbon chain, if we went just straight across, is 1, 2, 3, and 4. If we went straight here, 1, 2, 3, and then we could go up, which also would give us 4. If we went to the right here, 1, 2, and 3. So you do want to always check all your options, because sometimes people just kind of see the one straight in front of them and go with it. But sometimes, you could start at the bottom, come up and over. So a lot of times you do want to kind of look at, what is going on. Now, in this case, it is 4. And in this case, we do have 2 options to get to 4. My best recommendation would be if you have like a straight option there, like the guy straight in the middle of 4, you might as well go with that one, because it's sometimes easier to see everything else that's there. So we do have these 4 carbons in a row. And really, that's going to give us kind of the base of the name here. And the base of the name is going to come from 4 carbons. So as we saw in that list we just made, 4 carbons is butane. So the base of this name is going to be butane. And if we were doing this, by the way, over here on this guy, we would do the same. 1 carbon, 2 carbons, 3 carbons, and 4 carbons would be, again, our longest carbon chain. Now, when you find the longest carbon chains, a lot of times you will have some things that are not part of the longest carbon chain. So in this case, we have that CH3 group that is hanging out there. And if these are carbon groups, these are what are sometimes referred to as alkyl groups. And those are carbon-based groups. So why are they called groups? They're called groups because they're not part of the main chain, the longest continuous carbon chain. So they're like a group just kind of hanging on. And if we look at these groups, and especially if they're alkyl groups, you want to find your groups attached. They also will be based off of the first 10 alkanes in a lot of cases, based on how many carbons that you have. So when we look at this CH3 group that is hanging off of there, that is a 1 carbon group, which is based off of methane. And methane, though, is not a group. It actually has not 3 hydrogens, but it has 4 hydrogens, right? Now, this guy on the right there has only 3 hydrogens, and the reason for that is if I wanted to attach this methane the way it is to another carbon, can I do it by just adding a line there? I cannot, because now it has like 5 bonds, right? Too many. So alkyl groups are just like our alkanes, except that they are missing a hydrogen, and that allows it a place where it can attach into the main chain. So here the attachment is going to happen right here. And since it's an alkyl group and it's not really methane, we drop the last part of the methane, and this is what is known as a methyl YL, just like alkyl group. So that is a methyl group. If you had a 2 carbon group attached, it would be a ethyl group based off of ethane. If you had a 3 carbon group, it would be a propyl group based off of propane. So a lot of times the carbon groups that are not part of the main chain are named just like our alkanes, but we dropped the last part, put YL on it. So now we know that this guy up here is a methyl group. And this, by the way, a line with nothing at the end of it is always a methyl group in line structure. And that's because at the end of the line is assumed to be a carbon that should have 3 hydrogens to get the 4 bonds. So if you see again a line structure like we have over here, just a line, nothing at the end, it's not just a lonely line. It is actually a methyl group at the end there. There's a carbon that's happening there. So the other thing about naming things in organic chemistry is it's all about telling people where you could find everything, basically. So it's all about location, location, location. So when we have that longest carbon chain, we do have to actually number the carbon chain, and we have to number the carbons that's in that chain. So when we look at our simple example here, there's basically 2 options. We can number the chain, and we can number it left to right, which is 1, 2, 3, and 4. Our other option in terms of numbering here would be going right to left, which would be 1, 2, 3, and 4. So again, we could do the same thing here. 1, 2, 3, and 4 are 1, 2, 3, and 4. So those are your 2 options in terms of numbering. In the case of alkanes, what determines which way you should actually number is the groups that are attached. And the idea here, pretty much in most organic naming, is you always want to give the groups the smaller number. So the groups here with alkanes take priority. So we want to give that group the smaller number. Which carbon is it smaller? It is smaller going this way, right? And so we would want to number the chain in this direction. And in the case of my line structure, we actually want to number it in that direction, right? Which will give that methyl group a 2. And because it is a 2 there, we'll scratch out the other way here. We do have to incorporate that into our name. So this is what is known as 2-methyl. And then we just put it all together at this point. That is 2-methyl butane would be what we drew here. And when we go to name something, anytime there is a number to letter transition, you put a dash between it, or a letter to a number, you put a dash between the two. And if you happen to have two numbers in the name that go back to back, you put a comma between the two numbers. So commas between two numbers, dash between number and letter. By the way, if you have multiple groups, they are named in alphabetical order regardless of any prefix that there might be. So you put them all in alphabetical order regardless of the number. It goes alphabetical order and regardless of the prefix. Question on that there. Yeah. The numbering part? Yeah. So the idea here, especially with alkanes, and it does change as you go to different organic compounds, but in the case of alkanes, because all the carbons are single bonded, basically the priority in terms of the numbering goes to the groups that are attached. And you want to give the groups whichever way will give it the smallest number. And in this case, going right to left there on the guy on the left will give us the 2 versus a 3. And that's why we would want to go that way. By the way, once you lock in the numbering, you have to stick with that numbering for everybody else. So you can't just keep renumbering. So once you lock in whichever way you're going to number, any other groups that may be there are basically named the same or numbered the same way based off of that. Some other things in terms of groups. I have that. Let's see, where is that? So other things in terms of groups here is we could have some halogens. And halogens like Cl, F, Br, they're named very similar to, are pretty identical to how we, or even I as well, how we named it when we did our transition metals, right? So this guy is chloral, fluoral, bromol is how we named iodo for iodine. When we also look at carbons, for example, in terms of groups, it is important sometimes where the connection occurs. So when you look at a carbon, say something like this, when we look at this carbon, we could classify the carbons as being primary, secondary, or tertiary carbons. So that is sometimes a symbol for each of those: primary, secondary, or tertiary carbons. And the easiest way really to do it is to look at the carbon that you're looking at, and you want to see pretty much how many carbons are directly attached to it. So in this case here, this carbon that's in the box has one carbon that's directly attached to it. That is a primary carbon. Now, some people will teach you to look at how many hydrogens there is. So that's also another way that you can do it. But really just looking at the carbons is easier because it just tells you what it is, basically. So if you had something like this, and we look at this carbon right here, this carbon is attached to 1 and 2 carbons directly to it. This is what is referred to as a secondary carbon. And if you had a carbon such as this, this carbon here in the middle has 1 carbon, 2 carbons, and 3 carbons attached to it. This is a tertiary carbon. So primary, secondary, tertiary carbons can be identified by looking at the carbon and seeing how many carbons are directly attached to it, and you can classify it. So for example, when we get to something like propane here, which looks like this, And if we look at the carbons here, this carbon right here is a primary carbon. This carbon right here in the middle is attached to 2 carbons, which is a secondary carbon. And this carbon at the end is attached to 1 carbon, which is a primary carbon. So if we wanted to have a group like a propyl group, we could remove one of the hydrogens here at the end, actually either end, which are our primary carbons. And we could have an attachment point where it's going to attach at the end here. And this will be what is referred to as a propyl group. And the attachment is happening here at our primary carbon, basically. And you can do it at the other end. It basically be the exact same thing. You just turned around. But if we decided to attach here to our center carbon, which is our secondary carbon, we will end up with a group that looks something like this. And the attachment is happening right here at our secondary carbon. And this group has actually a special name. This is what is known as isopropyl group. And that's a historical name that's been used a lot for that group. It's really the attachment happening at the secondary carbon versus the primary carbon. So that's a group that you sometimes come across a lot in sort of condensed formula. You'll sometimes see it written like this. And that is your isopropyl group. You also have other groups as you go through, you know, things like T-butyl, which is where the attachment's happening up to tertiary carbon. Sec-butyl, which is happening at the secondary carbon, is where the attachment happens. So sometimes, depending on where the attachment happens, you could actually have the same number of carbon group, but it will be called something slightly different because it's a historical name and it's attaching at a different carbon. Any questions on that there? That's a very popular on isopropyl. Everybody loves isopropyl, like isopropyl alcohol, basically, right? Put an OH at the end there. You'll be good. All right. So let's just say we did have, for example, here. Let's try one here. Let's go with and let's actually do one more thing here. Hang on. A little editing here. It must do. All right. So why don't you give it a try? See if you figure out the name here. I'm going to try as well because I was just drawing things. Let's hope for the best here. Okay, so let's take a look. So we'll start with always the longest carbon chain. So we could start here, go 1, 2, 3, 4. We could go down 5 and 6. So that's 6. We then could perhaps go 1, 2, 3, 4, go up 5, 6, 7, and 8. That seems pretty good. By the way, just to check the other options here, you could start over here if you wanted to. Went 1, 2, 3, 4, 5, and 6, which is still less than 8. And you could also started here, went 1, 2, 3, 4, 5, 6, 7, which is pretty close as well. But I think it is going to be 8 there. I think it looks like a winner, and that is the longest. But again, you do want to kind of check all your options. So that's going to be our longest continuous carbon chain. That also means that if we're looking here, we have this is going to be considered a group that's hanging off of it. And that is going to be a group that is hanging off of it. Now, starting with our longest continuous carbon chain, which is 1, 2, 3, 4, 5, 6, 7, 8. That's going to give us really the base of our name, which is octane. We also want to identify what our groups are here. So this is a 2-carbon group, and 2 carbons is ethane. So based off of ethane, that would be a ethyl group. Again, it's going to have the YL ending because really it's missing 1 hydrogen to allow it to connect in. We have bromine here, which is going to be a bromol group in this case. Yeah. Any questions on that so far here? What is left is we want to do a little bit of numbering action here, I think. So we're going to number left to right. That's going to be a 1, a 2, a 3, a 4, a 5, 6, 7, and 8. Your other option is to number the opposite way there, and starting here, 1, 2, 3, 4, 5, 6, 7, and 8. So if we went that way in terms of numbering, we would have groups at 5 and 7. If we went in the blue direction there, which was our original numbering, we would have groups at carbon 2 and carbon 4. It is as simple as 2 is less than 5. Yeah, so that would be the way that we would want to go. So we would want to number this guy in this direction, as we always want to number in case of the groups here to give it the smallest numbering. So now that we locked it into place, we know that our bromine here is at carbon number 2. So that's like a 2 and a dash. We also know that our ethyl there is a 4 and a dash. And now we have pretty much everything that we need to name this. We're just going to put it together here. Again, alphabetical order, regardless of the number. So here we would look at the B versus the E. And that is the alphabetical order correct way. So this is going to be a 2 bromol dash 4 ethyl octane. Yeah. Give or take a syllable. Very close, I think. Yeah. Any questions, especially any questions on that there? It's fun stuff. Let's try a couple more. Why not? Let's do a little line action here. Now I'm just going to draw things. I don't know. Let's do that. All right, name both of those there. And we want to look for the longest carbon chain. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons. That's not too bad. Let's see here. We also could go starting here, 1, 2, 3, 4, 5, 6, 7, and 8. That seems longer. So 8 looks like a winner there. Again, the other option would be 1, 2, 3, which is not going to work so well. So again, it's not always going to be the straightest. So you do want to check all of your options there. And it looks like in this case, perhaps that is going to be our longest. That means that we actually have this as a group, and we also have this guy here as a group that's hanging off of it. So just like we did above, yes, I drew the same number of carbons there. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to give us the base of our name here is going to also be octane. We have a Cl group, which is a chloral group. And we have just a lonely line with nothing at the end of it. Remember, again, at the end of it is a carbon that has to have 3 hydrogens attached, which means that that is a methyl group that is happening right there. Now we want a number, and you could probably see that numbering left to right here is going to probably give us our smaller numbers of 1, 2, 3, 4, 5, 6, 7, and 8. Once again, if we went the other way, we have groups here at 3 and 5. If we started over here, that would give us groups at 1, 2, 3, 4, 4, and 6, which is obviously bigger. So we would want to go this way of numbering. That means my methyl group is at carbon number 3. And my chloro group here is at carbon number, looks like 5 in this case. Alphabetically, we're going C before M, even though the number is smaller and bigger. So that's going to give us a little 5-chloral, not 2, I was looking at the wrong number, 3-methyl, and then octane at the end of it. Yeah. Any questions on that one there? Looking at our guy on the right there, that is a cycloalkane. So the longest carbon chain is the cycloalkane. It is the entire thing there. And that is, again, if you count it up there, that is 5 carbons, 1 in each of these corners here. So 5 carbons is based off of pentane. Because it's a ring, that's a little cyclopentane action happening. That means that we have this guy and this guy, which are 2 lines, and they both are methyl groups, right? And that is actually 2 of the same group in the same molecule, which means we actually have to use a prefix for that. And the prefix for that is di for 2. So that is a dimethyl happening there. And we need to give the location. So in this case, we want to number starting at one of the methyl groups and going to the next one. Doesn't really matter which one you do in this case. They're both the same. So you can start at the other methyl, go in that way, which is a 1, 2. So this is a situation where even though it's the same group, and even if that same group happens to be on the same carbon, you have to give the number twice. So sometimes you may even have the same number, like 3, 3. So even if the same group is on the same carbon, you have to give the number twice. So this would be a 1, 2 number separated by a comma dash dimethyl and I'll try to fit it in there, cyclopentane. Question on that one there. Yeah. So again, if you have 2 numbers like you have here, and even if they are 2 of the same numbers, you got to separate them by a comma and give the numbers twice. Yeah.
What's the longest carbon chain include the methyls?
It would not in this case because that's sort of the main thing. It's whenever you have like a cycloalkane or whatever it is, that sort of ring structure is going to be the main part. Anything attached to it is considered a group in that case. Yeah. It is possible outside this. It is possible you could have like a benzene ring, for example. It can be like a group off of something else, but in this case, those guys are considered just to be off of it in most cases. Any questions on sort of the naming part here? So just to finish up on, if we had to draw something, right? Let's just say we wanted to draw something. I don't know. What do you want to draw? Let's do a 3-ethyl. I don't know. We'll do a 5. I'm going to regret this in a second. Methyl. Let's say we want to draw 3-ethyl, 5-methyl. I'm going to go with, let's go with our friend heptane. Or not. All right. So if you have this name and you want to draw it either the line structure or the condensed structure, if you're going to draw, say, the condensed structure, the way you always want to sort of draw things, if you have the name, is you always want to work backwards. So if you have the name, you kind of want to work backwards. And what I mean by that is when I see the name heptane, heptane tells me that there are 7 carbons. That's what hepta means, right? 7. So that's really what you want to start with, is you should just lay up 7 carbons, which is why I regretted it a second ago there. 1, 2, 3, 4, 5, 6, 7, 8. That would not be 7. That is 8. And now it's 7, I hope. 1, 2, 3, 4, 5, 6, 7. There we go. All right. Well, I got my 7 carbons. I'm not going to draw anything else, just the carbons. That takes care of that part of the name. I'm now going to go basically to what is left here, which is 3-ethyl, 5-methyl. Because I drew it, I can number this any way I like. I could call this carbon number 1 for me. If you want to call the other side carbon number 1, you could do that as well. So you could actually number whichever way you like carbon number 1. I'm going to do the one on the left here as carbon number 1. That means that's carbon number 2 next door. That's carbon number 3, carbon number 4, carbon number 5, carbon number 6, and carbon number 7. All right, so now I'm going to get rid of those numbers there. so they're not in the way here, what I'm gonna put down. All right, so again, for me, I'll just put a little 1 right there. That's carbon number 1, which means that carbon number 5, which for me would be right about there, I have a methyl group hanging out, which is a 1 carbon group that looks like that. That takes care of that. At carbon number 3, which for me would be right here, I have an ethyl group, which is a 2 carbon group. Looks like that. I'm out of name at this point. So everything else here is going to be hydrogen. And the goal here is what we talked about. Carbon needs 4 bonds. So we're going to put the appropriate number of hydrogens to get the 4. Guy at the far right end has only 1 line coming in, which means he needs 3 hydrogens to get the 4. The carbon next to it has 2 lines coming in, which means he needs 2 hydrogens. Carbon next to it has 3 lines coming in, which means he just needs 1 hydrogen. Guy next to it has 2 lines, needs 2. Guy next to it has 3 lines, needs 1. Guy next to it has 2 lines, needs 2. And the guy at the end there would need 3. There is my structure, I guess. Yes, as we go there. Could also do the same thing if you want to draw the line structure. Just start with the 7 carbons and just do a zigzag move. 1, 2, 3, 4, 5, 6, and 7. And again, if you call this carbon number 1, you would go down the road to number 5, which is 1, 2, 3, 4, 5. And that is where you would draw your methyl, which in line structure would just be a line. And you would go down to carbon number 3, which would be here, and draw an ethyl little 2 carbon action, and then you would have it at that point. Yeah. It doesn't. Usually they'll tell you like, hey, draw the condensed structure or draw the line structure. Or if they don't say, really, you can lay up anything you want. But probably when you guys, since you're going to take a real organic class, you probably will be drawing line structures most of the time, I would assume. Yeah. Other questions on that?